Today we're continuing with the bonding, and if you remember, we're discussing about covalent bond. Simple molecular structure in which the compound exists in the form of tiny molecules. In the previous class, we discussed the dot and cross diagrams in which we saw how the molecules are formed, how the electrons are shared, how the different molecules are formed, in which we also discussed the expansion of octet and all that. So the examples, if you remember, H2O, CH4, the tiny molecules, whenever the covalent bond with the simple molecular structure is formed. Today we are continuing the molecules which we had the dot and cross diagrams. Today we are going to see the shapes of those molecules. Let me give you an example that, for example, we had the dot and cross diagram for the water like this. Right? Okay, so this is dot and cross diagram for the water. So today what we are going to see, what will be the shape of water? Will the water molecule look like this? Will the water molecule look like this? Or any other? The shape of water molecule today we have to see. Okay, so this is how the topic for the today, that how the shapes of the covalent molecules look like. Okay, so heading there, shapes of covalent molecules. Now the molecules are so tiny that we do not have any microscope or an instrument which can lead us to see how a molecule looks like, right? So we have to predict shapes on the basis of a theory. Okay, that is the theory used here is known as write down please. Yes, Weisser theory. Right, write down the shapes predicted on the basis of theory known as valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory, VSEPR. Now, what this theory says, as I said, we cannot see them, how the molecules look like, so we have to predict on the basis of this theory, valence shell electron pair. As the name tells us, what this theory says, for example, let me give you the examples. For example, if I have beryllium chloride molecule, and I need to see what of this molecule. Now listen, for example, look, what the Weisser theory says. The Weisser theory says that if you draw the dot and cross diagram, for example, this is Be. Beryllium is in group 2, having how many electrons? 2. Okay. It shares the 1 electron with chlorine, 1 electrons with chlorine. Okay. Now, this is 2 electron pairs which are shared. So what the Weisser theory says, that's quite a commonsensical, that these 2 electron pairs, obviously what they are going to do, they are going to repel each other. Yesterday, we also saw when we were looking at the expansion of octet, the atoms around the center, obviously they are going to repel. And when they're going to repel, they are moving apart from each other like this. And they adjust themselves in a position or at a point where they have minimum repulsion and maximum distance. So with which point they have a minimum repulsion and maximum distance? What do you think? Once they are repelling each other, so where is the point? This will be the point, for example, here. Once they go to this point, this is beryllium. Look, here. Once they are exactly opposite to each other. Am I right? This is the point where they have minimum repulsion and maximum distance, right? So on this basis, the beryllium chloride molecule will adopt the shape like this, in which two chlorine atoms are exactly at 180 degree from each other. And this is the angle between these two bonds. And what is this angle? 180 degree. And what is the shape of this molecule in this case? It's a linear. So I hope you understand what I'm trying to say, that whenever the central atom of molecules, the electron pairs around it, the central atom, they repel each other and they themselves at distance where there is a minimum repulsion and maximum distance, right? So in this case, this is not specific to beryllium chloride. Whenever they have two electron pairs, two bond pairs, they repel each other and go to this distance, right? For example, now look at this. If let me give you one more example. Let's say we talk about BF3. This is boron. Boron is in group 3. The central atom, 1, 2, 3. So 3 fluorines bond like this. Now they are again what? There's a repulsion and they are repelling each other. Yes. And go at which distance? Yes. They go as far as they can. And then this is the place where they have a maximum. Look. Yes. So they go like this. Here, here, here is the fluorine, here is the fluorine, and here is the fluorine, right? So this is the point, look, where they have like this. So this is boron. So what do you think? What does this shape look like? Yes, does it look like a triangle? Look. And what is the bond angle, do you think? All they are in a one plane. So over one plane, the whole circle makes 360. So this is 120 here, 120 here, and 120 angle here. Okay. So this is how the 120, 120 is this. Okay. Right. So this is 120. Okay. So this is how we look like. So it means what I'm trying to summarize here, what the theory says, that you draw the central atom, you draw the molecule and look at the central atom, how many electron pairs, they repel each other and arrange themselves at a distance where there is a minimum repulsion and maximum distance, right? And on this basis, we predict the shapes of covalent molecules, right? So I'm going to make a table at this point before I move on, and then we'll put the examples in this table. The table should be looking like this. Look, here you have to write electron pairs. Here bond pair. Here lone pairs. Shape. Bond angle. Look at this. Now, for example, in this particular case, what we said, that there were two electron pairs around the central atom. Both of them were the bond pairs, zero lone pair. The shape was linear. And what's the bond angle? Between the two bond was angle 180. Similarly, if there are three electron pair, three bond pair, zero lone pair, what was the shape? Trigonal, planar, with a bond angle of what? 120. This shape, you can call it trigonal planar or trigonal planar, right? So it looks like a triangle. And this is the shapes. This is how we predict the shape of the molecules, right? So it's like this. Let me explain it again. Here. So this is the table which we have to follow. So the shape of a covalent molecule is predicted by the number of electron pairs around the central atom of a molecule, right? And what is the logic? They repel each other and arrange themselves. So I'm going to write them in words here. Although we don't need them in words, but we should write the shape is predicted by the number of electron pairs around the central atom of a molecule. Around the central atom of a molecule. And what is the logic? The electron pairs repel each other and arrange themselves at a distance where repulsion is minimum. As I said, the examiner don't need you to write these wordings. This is for our own, yes, reference. So we just have to draw the diagram and we just should be able to identify what is the bond angle, right? So now this is not limited to these molecules. Now I'm going to write two other molecules. You have to predict the shape of these two molecules, which I'm going to write right here. So what you will follow, you will first draw the dot and cross, then you will see the central atom around, how many electron pairs, and then you will predict the shape of that molecule. Okay, here you go. For example, the next one is aluminum chloride, AlCl3. Please predict or not predict, draw the shape of aluminum chloride and carbon dioxide. Bond angles and shapes of these two molecules. First of all, we need to have the dot and cross diagrams. Aluminum is the central atom. There are three chlorines attached with it, like this. So now I can identify there are three electron pairs around the atom, and all three are the bond pairs. They repel each other and arrange themselves at a distance where the repulsion is minimum. And that is what is that place? Yes. So when the examiner asks you to draw, you have to draw like this, okay? And then these dotted lines just to make sure that you have drawn a trigonal planar with a bond angle of what? 120. Please mind this difference. This is dot and cross. When they ask you to draw the dot and cross, this is the in dot and cross. You see, I have not maintained any bond angle. Right, dot and cross. You can draw any like shape you want to, but in shape, when they ask you to draw the shape, you have to follow this pattern. Proper angles you have to show. Now look at the carbon dioxide. Anyone done with the carbon dioxide? Yes. Once you draw the dot and cross, you see there are double bond in carbon dioxide on this side, double bond on this side. Now, as we see, there are two bond pairs on each side. But what we do, we have to take two bond pairs. Now listen, everyone, as a one bond pair. In Vesper theory, although these are the two bond pairs, there's no doubt here. But once you are predicting the shapes, as the electron clouds repel each other. Na? So this cloud is going to repel this cloud. That's why once you are looking into the shapes, then you have to take double bond, triple bond, or a dative covalent bond as a one bond pair, just for this theory. Okay, so please write down in this theory double, triple, or dative bond considered as one bond pair. So if this is one bond pair, so now these two bond pairs repel each other. So when there are two bond pairs, we know that they repel each other and arrange themselves at a distance of 180 degree. Okay, so this is and this is okay. So linear with the bond angle of what? 180 degrees. So please keep in mind whenever there's a double, triple, or dative bond, we have to take it as a bond pair. Okay. For example, if I ask you again, sulfur trioxide, can you please tell me the shape of sulfur trioxide? SO3. What is the shape of SO3? First, I have to draw the dot and cross. Three double bonds around the central atom. One double bond is considered as one bond pair. So if there are three bond pairs, so what will be the shape? Trigonal pair. So this is how we look at the shapes like this. Now, moving on. Any question up to this point? So sulfur trioxide, carbon dioxide, aluminum chloride, boron trifluoride, and beryllium chloride. These are the molecules, the shapes we have already considered. Okay. So if I show you like this, can I have a pen, please? So यहाँ भी मैं video on कर देता हूँ. Those who are on the Zoom, they can see my video. Look, what I'm trying to say. One more. What I'm trying to say, the point where I'm holding is the central atom. This is one bond pair, this is another bond pair. So when two bond pairs around it, they repel each other. And this is the point where they have minimum repulsion and maximum distance. If they get this side, then again distance less, so repulsion more. So this is the point. This is one bond pair, this is another bond pair. What is the angle? 180. Now, if there is three bond pairs come around it, here, the third one, then they all repel each other. And they have to go like this. So what is the angle now? 120. 120. This is a one fluorine. Let's say this is BF3. This is one fluorine and this is another fluorine. And these are the bond pairs. Right? So this is the angle. So this is a triangle like this. 120, 120, 120. And they all are in one plane. They are all in one plane. Now my next question, look at this, if I remove this, now listen carefully. If I remove this atom, let's say it was sulfur trioxide. What was this? Sulfur trioxide. One oxygen, one oxygen, one oxygen. It is a sulfur trioxide. Now I removed this oxygen. Now it is sulfur dioxide. What is this? But I removed oxygen, but I obviously cannot remove the electron pair present here. That turns into obviously a lone pair. So what do you suggest about this? If there are two bond pairs and one lone pair is like this, it is still applying the force on the both sides. It is still repelling these electron clouds, the bond pair clouds. Electron is electron, it's a cloud, like either lone or a bond, but there is no atom. So one thing that changes, which I know, that there is no third corner. There were three corners now, one corner is gone. But the cloud is still there. So we are expecting the same angle because the force of attraction is there, force of repulsion is there. So we are expecting the same angle, right? But one thing which we have to consider is this, that the lone pair actually occupies more space. What is the meaning of more space? If it was a bond pair like this, so 120, 120, 120, equally spaced, but when it turns into a lone pair, more space they occupy. Well, how can they occupy more space? By pushing these two bond pairs close. So that's why they have more space. How much close they're going to push? Yes. So we actually, maybe any number, less than 120. There was a 120. But we have to assign a number at this point. So what we believe, or what we think, and what we consider, that whenever the lone pair comes, it pushes the bond pairs close at least 2.5 degree. At least. So initially, when they were all three bond pairs, the angle was 120 here. But when it turned into lone pair, it pushed them close. So 2.5 less than 120 is 117.5. So one thing, that when the lone pair comes in, the angle between the bond decreases. How much? 2.5. If two lone pairs come in, then 5 degree, obviously. One thing. And secondly, the shape is no more three-cornered. Shape is no more trigonal. Shape is now what? It's like a English letter V. If you look at this, it's a bent, angular, or non-linear, you say, right? So whenever we have three bond electron pairs around the central atom, but one of them is lone pair, so the shape changes, the bond angle changes, right? So let me explain it here now. I'm going to throw it. Now look at this. What I'm trying to say, pay attention. Look, for example, look, pay attention. What I'm trying to say, if you look at sulfur dioxide, please pay attention and draw the dot and cross diagram. Here is the sulfur, 1, 2, 3, 4, 5, 6 electrons. Here is the double bond. Here is the double bond. So what is this? This is sulfur dioxide. Now, how many bond pairs? Yes, these are the two bond pairs. And what is this? Yes. So what I said, that lone pair occupies what? More space. So lone pair is going to push these two bond pairs close. How much close? Initially, we were expecting 120, and now less than 2.5 degree less than 120. So it should be like this. What is the angle here? 117.5. Okay. So this is how it looks like. Okay. Shape is non-linear. V-shaped. Bent or angular. Next. So whenever, now let me put it in the table. Go back to the table. Whenever there are three electron pairs, two bond pair, one lone pair, the shape will be what? Non-linear. Yes, and angle will be 117.5. Okay, now come to the next. This is methane. CH4. Yes. If you look at the methane, 1, 2, 3, 4 carbon, 4 hydrogens. So how many bond pairs? Right. Now, how they're going to arrange themselves with the 4 bond pairs? Now look at this, everyone. If we look at the 4 bond pairs, so ideally what we were expecting, ideally what we were expecting, look at this. Please pay attention. It should be like this. What we are thinking, it should be like this. So bond angle of Minahil, I need your undivided attention, please. Right? So if you look at this, please pay attention. The bond angle should be 90, but actually this is not the case. Because we talked about this the other day, the steric hindrance thing. When they come too many electron pairs, the too many clouds in one plane, there is a steric hindrance. They cannot exist in one plane, right? Because let's say we're talking about this. So this electron pair and this electron pair, they're pushing it. So if it goes in this side, there's a repulsion with this. If you go on this side, there's a repulsion with this. So in order to increase the space and create a more gap, an angle, it has to get out of the plane. So after 3 electron pairs, they can't be in one plane. They have to go out of the plane and becomes 3D. 3D mean now this is going out of the plane. Now it is pointed towards you like this. This going inside the plane, it is pointed towards me. This shape becomes three-dimensional now. Here is the plane. So this one is bulging out of the plane. Now, if I put it like on the whiteboard, this one is coming out of the whiteboard, this one is going inside the whiteboard, and these two are hanging with the whiteboard. Right? And this shape is known as tetra, mean four, it will mean corners. So four cornered now. Right? But the angle, which yes, is not 90. Obviously, they have to go out to increase the angle. So 90 se to zyada should be there. तो कितना है 109.5 and this shape is known as tetrahedral. So whenever there are four bond pairs, four electron pairs, all four of them are bond pairs. So angle is going to be 109.5 and the shape is three-dimensional tetrahedral. Now, over here, before I go on and draw this, let me explain the other parts as well. If this one turns into a lone pair,
सर
yes,
आप कुछ दिखा रहे हैं क्योंकि नजर नहीं आ रहा.
आपको वो व्यू चेंज करना होगा बिकॉज साथ वाली विंडो में वो नजर आ रहा होगा.
नहीं सर, वो ब्लैक हुई हुई है आपकी स्क्रीन.
अभी देखिए.
अब आ रहा है.
Okay, now this is the look. This is how it looks like here. Here, ये tetrahedral shape है. This is out of the plane. This is inside the plane. These two are along the plane. Angle is what? 109.5. What I said, and this shape is tetrahedral, and it is three-dimensional. What I said, if this one turns into a lone pair, so one thing that happens, there are no more four corners. How many corners now? Three corners. So it's not tetra, it's a tri. Right? One thing changed, it's now trigonal, not tetrahedral. And secondly, what the lone pair does, it's going to push them close. If the angle was 109.5, now 2.5 degree less, the angle is going to be 107. So that this shape, if there are three bond pairs and one lone pair on the top, it's going to be 107 trigonal pyramid. They are no more in the plane. They're like a pyramid. Look, if I put it down, so they're like a pyramid. And secondly, adding on to that, if there is another lone pair that turns into a bond pair turns into a lone pair, this one. Now there are two lone pairs around it and two bond pairs. Obviously they're going to push them close. So 107 was the angle. Now 2.5 degree less should be 104.5. So this is the angle, and this is non-linear V-shaped pentacular, right? So we had this shape before, but that was like this with angle of what? 117. Now this is what? With angle of 104.5, right? So what I'm trying to say, again repeating, look, if there are four electron pairs around this four bond pairs, shape is tetrahedral. If three bond, one lone, shape is trigonal pyramidal, angle is 107. If there are two bond, two lone, the angle is 104.5 and the shape is non-linear. Got it? And as the bond pair turning into the lone pair, the angle between the bond is getting less and the shape is also changing. Tetra to tri to V shape. Okay? So now let's see the examples of all these, right? Before moving on, let me give you the examples. Here is the first one is CH4. Look at this. So how many electron pairs around the central atom? 4, and all 4 are what? Bond pairs. So 1. Look, and this is the tetrahedral shape. Now, how to draw this shape of tetrahedral? Right? So we have to draw like this. Now, obviously, we can't show it until we have a unique kind of lines which are telling which one is going out and which one is going in. So this is what we are going to do. If we put a triangle, that means we are trying to say that this one is coming out of the plane, this one is going inside the plane, and here it is, two along the plane. This is CH4. Okay, so bond angle is 109.5. Shape is tetrahedral. So whenever, this is not limited to CH4, whenever they have four bond pairs around the central atom, they organize themselves. And this three-dimensional triangle mean coming out of the plane, and this is going inside. Next, for example, let's say ammonia. If I ask you what is the shape of ammonia molecule, you see, you are gonna draw the dot and cross. Here is the dot and cross. How many total electron pairs? Four. Out of four, three bond and one lone. So kind of this bond is actually gone in ammonia, just for the sake of argument I'm saying. So what is the left behind is the shape of the ammonia. So one out of the plane, one inside the plane, and one along the plane. It's like a pyramid. Yes, so this is along the plane. This is coming out of the plane. This is going inside the plane. So angle is 107, and the shape is trigonal pyramidal. Similarly, if you have water, H2O, what is the shape of H2O? Oxygen has 1, 2, 3, 4, 5, 6. Okay? Yes. Two lone pair and two bond pairs. Yes. One of 4.5, because here they are going to arrange. Look, here are the two lone pairs, here and here. So they are going to push them apart. So more space they are going to take. We have the lone pair repulsion, bond pair, lone pair repulsion. So that sequence we can use, but here it's not the part of the syllabus. So I just told you they take more space. When they take the lone pairs more space, they're going to push the bond pairs close, right? So the bond pair which were actually in the original shape were 109.5. Now have come to very, very close and 100, 104.5. And this shape is again non-linear, bent, angular, or V-shaped, you can also call it. Right, so now I'm going to add this into the above table. So we could memorize it here. For example, look, if there are four electron pairs, four of them are bond pairs, zero lone pair, the shape is tetrahedral. Angle is 109.5. If four electron pairs, three bond pair, one lone pair, trigonal planar, trigonal pyramidal. My apologies. With a bond angle of 107. And if there are four in total, but two bond and two lone, it will be non-linear with a bond angle of 104.5. Okay, so these are the three with, yes, four electron pairs in total, in which two bond pairs and two lone pairs. right? Similarly, for example, now let's move on to this. Before I move on to this, I would like you to draw a few diagrams here. Uh, Ammonium ion. I need you to show the bond angles and diagram for the ammonium ion, for oxonium ion. Please, we just had the previously yesterday we had the dot and cross diagrams. Can you use them to see and draw the diagrams? Three examples, Vichu. Quickly. What about the ammonium ion? Why? Because there are three bond pairs like this, and we just learned yesterday that the hydrogen with nitrogen with H positive, the bond is a covalent bond. Just the only difference that the shared pair of electron belongs to nitrogen. Now these four bond pairs, so it's gonna be tetrahedral with 109.5. What about this? Why? Because there are one dative, two covalent, and one lone pair. So three bond pairs and one lone pair. So three bond, one lone, trigonal, pyramidal, right? And then H2S, quickly, please. Non-linear. Here, 1, 2, 3, 4, 5, 6. So here is the bond, here is the bond. So how many bond pairs? Two. And how many lone pairs? What is this? 104.5. And what about the last one? Linear? Why? Okay. Here. So if you look at this, one bond pair on this side and triple bond is also considered as one bond pair. So how many bond pairs? Two bond pairs. So when two bond pairs, they repel each other like this. And what is the angle? 180. And what is the shape? Linear. So it's a linear shape with a bond angle of 180. So we are gonna stop here. And then we have still more the expansion of octet, PCl5, six bond pairs, five bond pairs around the central atom. We'll continue this and we're going to stop here for a while. Okay. And listen, tomorrow is the test.